Hey guys, I'm Jade. Today is my LeetCode review one-take vlog on 222nd problem. Count complete tree nodes. We are given the root of a complete binary tree. We have to return the number of the nodes in the tree. According to Wikipedia, every level except possibly the last is completely filled in a complete binary tree. And all nodes in the last level are as far left as possible. It can have between 1 and 2 raised to the power of h nodes, inclusive at the last level h. We have to design an algorithm that runs in less than big O of n time complexity. Let's see the example 1 here to understand this problem easily. We got an inputted binary tree here, and it has 6 nodes, so our output is 6. And if the binary tree is null, we return 0. And if the binary tree is only have one root node, our output is 1. And then let's get started with our intuition to solve the problem. First, we can easily use the depth first search, recursively or iteratively, and the breadth first search algorithm to solve the problem with big O of 1 time complexity. But we need to do it more efficiently than big O of n, as the problem asks for. And a complete binary tree has properties that all levels except the last level may not be completely filled, and all nodes on the last level are as far left as possible. So we can leverage its properties to improve the algorithm's time complexity. And there are two approaches. The first approach is called recursive solution or recursion, and will utilizes the tree's height to calculate the number of nodes. And the brief idea is we'll compute the height of the left and right subtrees recursively. And if the left and right subtrees' heights are the same, which means the left subtree is a full tree, so we can calculate its size directly. And we'll recursively count nodes in the right subtree. And on the other hand, if the left and right subtrees' heights are not the same, which means the right subtree is a full tree, so we can calculate its size directly, and we'll recursively count nodes in the left subtree. And then let's get started with our code to solve the problem. First, we need to declare and implement a helper method to calculate the height of the tree. So the code is private integer and get height, and we need a root node of this binary tree. So the input parameter is a tree node, and inside the method body, first we'll create a local variable, let's say height, starting at 0, and then we'll create a while loop to traverse down the leftmost path to calculate the height. While node is not null, and then we'll increment the height variable, and we also have to move down the node pointer, which is node is assigned to node.left. And then out of the while loop, we just return the height. And the final result is the number of nodes from the root node to the leftmost leaf node. And then we just have to implement the count nodes method. Oops, we need a semicolon here. And inside the count nodes method body, first we have to handle a bad case. If the root node is an is null, then we'll return 0, because which means is an empty tree. So if root equals null, we'll return 0. And then we'll calculate the height of the leftmost path from the left subtree and the right subtree. So integer left height equals get height of root.left, and is very similar for the right subtree. So integer right height equals get height of right root.left.right. And then we have to compare if the left height equals the right height or not. And if they are the same, which means the left subtree is a for tree. So the code is if left height equals right height, which means the left subtree is a for tree. So we can directly calculate its size directly, which is 2 raised to the power of h and minus 1. And h is the height of the left subtree. So which is 2 raised to the power of h, and we have 2 minus 1. But we also have to plus 1 to count for the root node. Plus 1 for the root node. So overall, the code should be returned, and the 2 raised to the power of h is computed by 1 left shift by left height with bitwise left shift operator. So the code is 1 bitwise left shift operator and left height. And we have to subtract the 1, and also we have to plus 1 for the root node. And then we have to recursively count nodes in the right subtree, because we don't know if the right subtree is a full binary tree or not. So we'll recursively call the count nodes method. Count nodes with root.right. And that's the first situation or first condition. And if the left height is not equal to the right height, which means the right subtree is a full tree and the left subtree is not. So we can directly calculate the nodes of the right subtree, and we have to recursively to check for the left subtree. And the code is very similar. Return 1 with the bitwise of left shift operator and right height. We have to subtract 1 and plus 1 for the root node, and we have to recursively call count nodes method with root.left, which means the left subtree. And that's all the code for the first recursion algorithm. Let's submit the code and check for the correctness, and then I spelled it wrong, so I have to revise it. Let me resubmit it again and check for the correctness, and then let's analyze the time and space complexity. Yes, our code got accepted. So the time complexity are composed of 2 steps. First, the height of the tree, it is big O of log n. And for each recursive call in each level, we need to compute the height. And this step takes another big O of log n. So the overall time complexity, it is big O of log n of n squared. Big O of log of n squared. And the space complexity, it is log of n. This is because we use the recursive call stack in a balanced binary tree. And this is the first approach. Let's get into the second approach, which is called the iterative approach. And then let's get started. Second approach, iterative method. First, we still have to declare and implement a helper method to help us calculate the height of the inputted tree. And code is private integer get height. We need a tree node as an input parameter. Tree node, and inside the method body, first we'll create a local variable. Integer height starting at 0, and we need a while loop to check for if node is equal to null or not. And inside the while loop, first we have increment the height variable, and then we have to move down the node. Node equals node.left. And out of the while loop, we just return the height. And then inside count nodes method, first we still have to handle the bad case. If root equals null, we just return 0. And then we'll create several variables to help us solve the problem. First, we'll create a local variable, node count. Node count started at 0. And we need another variable, let's say current pointer, starting at the root node, as we need to traverse the whole tree. Current started at the root node. And then we'll use a while loop to traverse the tree to simulate the recursion, like we did in the first approach. While current is now equal to null, and inside the while loop, first we still have to calculate the height of the leftmost paths from the left subtree and the right subtree. The code is left height equals get height of, oops, I spelled it wrong, current variable. Current dot left, and it is similar for the right height. Right height equals get height of current dot right. And then we have to check if the left and right heights are the same or not. If so, which means the left subtree is a full tree. But the code is if left height equals right height, which means the right subtree or left subtree is a full tree. We can calculate its size directly, which is 2 raised to the power of h and subtract 1 nodes. 2 raised to the power of h and subtract 1. And h is the height of left subtree. And we need to plus 1 for the root node. So we have to increment the node count variable by the sum of the two numbers. And the code is node count implemented by one and bitwise left shift operator, a double open angle brackets, and left height, subtract 1 and plus 1. Oops, I spelled wrong. Node count. And then we have to update the current variable and set the current node, the current variable, to the right subtree, as we need to compute its number of nodes in the next iteration. current equals current dot write. And on the other hand, if the left height is not equal to the right height, which means the right subtree is a full binary tree. So we can calculate nodes in the right subtree directly, and it is very similar. The code is node count incremented by 1 and a double open angle brackets with right height -1 and +1 for the root node, and we'll set the current node to current dot left, so we can calculate its remaining number of nodes in the left subtree. And out of the while loop, which means we have traversed all the nodes we have traversed all the height in the left and the right subtree recursively. So we just return the final node count variable. Return node count variable. And that's all the code for the second approach. Oops, while current cannot find symbol. Current, we have the revised name of current variable. Left is now on the line 21st. Node dot left. I'm sorry, the condition is incorrectly. Let's revise it and resubmit the code. Yes, our code got accepted. And then let's analyze the time and space complexity. So the time complex is still composed of two parts. First, the height of the tree, it is big O of log n. And for each recursive call in each level of the tree, we compute the height, which takes another big O of log n. So the overall time complexity is big O of log of n squared. And the space complexity, it is big O of 1, as we just created one local variable, which is the node count variable, to help us sum the number of nodes, and we avoid the recursion stack, which we used in the first method. And thank you guys for watching. This is my LeetCode review vlog on the 222nd problem, can complete tree nodes. You can visit, I highly recommend you guys to visit my online GitHub page here, which contains all the problem description, main idea, and Java code with very detailed explanation and the final time and space complexity analysis. You can also visit my GitHub repository here, which contains all the codes and nodes to build this online GitHub page here. And I'll put those two links on my YouTube description below. And thank you guys for watching. See you next time. Bye bye.